This BBC podcast is supported by ads outside the UK.
I'm Julie Andrews, and it is my great pleasure to bring you Jane Austen Stories, the new show from the Noiser Podcast Network. I'll be reading Pride and Prejudice. We'll walk grand estates and take tea with well-dressed gentlewomen. But in this tranquil corner of England, not everything is quite as it appears. Listen to Jane Austen Stories wherever you get your podcasts.
Now, to mark the end of his 27 years this month of presenting In Our Time, we have Melvyn Bragg to introduce the first in a series of his most cherished episodes.
One of the pleasures of In Our Time for me is that it's become the university of the airwaves. Each week I and countless listeners have been marvelling as three brilliant academics share their expertise on history, culture, philosophy, science and religion, no subject too great or small. We've made almost 1,100 episodes, each a favourite, but we can only have a few for this occasion. So let's start with this one from 2011 on the moon, an object so familiar and so full of mystery. And we have such wonderful guests. In this episode, for example, sitting opposite me in the studio one Thursday morning was the man who co-discovered the first black hole. Hello, on November the 30th, 1609, Galileo Galilei pointed his telescope at the moon. He was astonished by what he saw. "I found the surface of the moon," he wrote, "not to be smooth, even and perfectly spherical, but uneven, rough, and crowded with depressions and bulges. And it's like the face of the earth itself, which is marked here and there with chains of mountains and depths of valleys." Galileo was the first human being to report these features in such detail. But the moon, with its power over time and tides, has fascinated mankind for millennia. Locked in an orbit 250,000 miles away, our closest neighbour in the solar system and our only natural satellite, the moon exerts a powerful influence on life on Earth. More than 70 spacecraft have been sent to the moon, and although we've now walked on its surface, there are still many things about this 4.5 billion-year-old hunk of rock that remain a mystery. With me to discuss the moon are Paul Murdin, Visiting Professor of Astronomy at Liverpool John Moores University, Caroline Crawford, Gresham Professor of Astronomy and Outreach Officer at the Institute of Astronomy at the University of Cambridge, and Ian Crawford, Reader in Planetary Science and Astrobiology at Birkbeck, University of London. Paul Murdin, what is the moon?
You described it well in your introduction. It's the satellite of the Earth. It goes around the Earth just as the Earth goes around the Sun. Actually, that vocabulary puts the moon in a kind of a subordinate position, and it might not really be like that. The moon is smaller than the Earth, but it's a quarter of the size of the Earth, and so it's comparable to the Earth. And you could say that the Earth and the moon form a twin planet that goes around the Sun. The orbit of the moon has a radius of about 350,000 kilometres, 250,000 miles, pretty much circular. And the moon goes around the Earth once every month, hence the name of the unit of time, the month, associated with the moon. It's spherical, pretty much, slightly flattened at the poles. It's a bit pointy, like a pear, and it points towards the Earth. The lump on the side points towards the Earth, and the Earth has a kind of grip on that point. And so the moon always keeps the same face towards us. So when you look at the moon, you can always see exactly the same arrangement of grey and bright patches.
What do we know of its composition and its climate?
Its climate is simple to describe because it doesn't have one. It's airless. It's either very hot when it's in the sunlight or it's very cold when it's...
very being what?
Can't remember.
Very, I think, is 108... and I can't remember.
Its composition, well, its density is very much like the density of the rocks on the crust of the Earth. And that's pretty much what it's made of. It's made of the ordinary kind of minerals that you find in the crust of the Earth, things like basalt.
Since the prehistoric times, the moon seems to have had an influence on human culture. Can you tell us about the early evidence of men and women being intrigued by the moon and using it for the beginning, it would seem, of intellectual thought?
The most noticeable thing that you can see about the moon with the naked eye is the fact that it's got phases. the bright part, the bits that's lit up by the sun, changes in aspect relative to the Earth, so that when the moon is in front of the sun, in the same direction as the sun, it's the back of the moon that's illuminated, and you see the dark face of the moon there. When the moon is behind the Earth, away from the sun, you can see the whole hemisphere, and so it's full. And so you see the progression of phases from dark to crescent to half moon to full moon, and then back to a new moon again. And that's a pretty obvious thing to notice. And mankind must have seen that right from the very earliest times. And in fact, the earliest observations of any astronomical phenomena that now still exist are observations of the phase of the moon. There are 2 fragments of bone that have been dug up in archaeological circumstances. One, a piece from some caves near Dordogne, and one, a piece of bone that was the handle of a knife that was found in Africa. And these date from about 20,000 years ago. And each of them has got scratches or marks on it, which run in cycles of 29 diagrams of the phases of the moon, in groups of 29 running over about 3 months. So 20,000 years ago, there were people who were making notes of the phases of the moon for some reason. In the case of the bone handle, it might have been a hunter that was off on a journey, wanted to find his way back home in time, or it might have been a woman who was keeping track of her menstrual cycle and her fertility for some reason.
Sir Carolyn Crawford, we could characterise this as the beginning, the first evidence, or early evidence of intellectual activity among people who became us.
Yes, and certainly the importance of the moon for the timekeeping continues in terms of longer than a month or so, looking at the extreme of when the moon rises and the moon sets in a year. So by the time you get to prehistoric times, you have 7,000, 3,000 BC, you have structures like Stonehenge, which give you permanent observation points to monitor the moonrise and the moon set. And as Paul says, you start off with the idea of a lunar cycle establishing a month, which eventually gets divorced from the calendar month that we use nowadays. But nonetheless, we've still got this powerful pull about the importance of the moon for the activities that we carry out.
It's taken a lot of cultural associations. There's a harvest moon, the blue moon, the hunter's moon. Could you develop some of those?
Yes, certainly, because again, if we go back several centuries, having a full moon at night is crucially important. It illuminates. If you're travelling, it makes your travelling safe. If you're a farmer, if you have a full moon, it's enormously helpful when you're gathering in the crops, and particularly you have this phenomenon of what we call the harvest moon that happens around the September equinox, because what happens is the moon rises about an average 50 minutes later each day. Around the September equinox, it's only rising like half an hour later each day. When the sun sets, the full moon rises, and you get this period of a few days in a row where as the sun sets, you get a full moon rising very soon afterwards, allowing the workers in the field to continue working, bringing the crops. So that's your harvest moon. And there's a similar thing a month later with the hunter's moon, where the moon can again help hunting late into the night around the period of the full moon. So it was illuminating activities. You mentioned blue moon. I mean, that arises from observations of the moon, and again this period of behaviour. And the way we look at it now, it's this occasional occurrence when you get 2 full moons in 1 month. So if we say once in a blue moon, it's something that doesn't happen very often. And you have the moon going around its lunar cycle every 29 days, and you get 12 of those in a year, but there are 11 days left over. So the 12 lunar cycles don't fit into the 365 days of our year. So after about 2.5 years, you've accumulated enough days that you can pack in an extra lunar cycle, and every so often you get 1 month with a full moon at the beginning and the end of the month, and that second moon is now the blue moon. So again, this idea of once in a blue moon again is a very rare occurrence.
I was just thinking of rather gentler pursuits than hunting, and because there was a great fashion for moon walking, and in the Lake District at the time of Wordsworth, they would go out and read by a bright moon, read their poetry. And I just sit, I'm a place of that, and I went and sit to see if you could read by a full moon. You can very well, even me with my eyes that aren't so good. So there's reading by a full moon as well.
Okay, well that's brilliant. It's another example of just again how important the full moon was to our predecessors.
Can you tell us how, we all know the tides are dictated by the moon, but can you tell us how that works and how that deeply affects our planet?
Well, yes, we've long since known that the tides are affected by the phase of the moon, and it's to do with the gravitational pull of the moon. And it's not just the fact that the moon pulls on the waters of the Earth, but it pulls differently on the waters on the near side of the Earth, near side to the moon, than on the far side. So, for example, when you think of moon's gravity, you have to realise that it drops off very sharply with distance from the moon. So if you look at the water on the near side of the moon, so on the side of the Earth nearest to the moon, is getting pulled to the moon more strongly than the Earth underneath it. So it rises up to form a bulge of water that then basically follows the moon round in its orbit around the Earth, but meanwhile the Earth is rotating under it. So that tide, that bulge, appears to travel across the surface of the Earth. It's being pulled around by the moon. But of course there are two tides in every day, and you have an equal and opposite high tide, because not only is the near side of the ocean being pulled towards the moon, you also have an effect that on the far side of the Earth away from the moon, the Earth is being pulled to the moon more strongly than the water on that side, and you have the water was left behind to create a second high bulge within the oceans.
So as Paul said at the beginning of the programme, they do seem to be a system in themselves, a twin system. Without the moon making the tides, making the climate, the sort of life that we know would probably not exist on Earth.
Certainly it's been very important for the development of the Earth, and these tides are a crucial part of the pattern of the Earth and the climate, as you say.
Ian Crawford, how's the moon influenced by the Earth?
Well, it's reciprocally, really, because, as Paul said, the Earth-Moon system really forms a double planet. So just as the moon raises tides on the Earth raises tides on the moon, except they're about 20 times stronger. So the consequence of this is that the moon has become tidally locked to the Earth, so it can no longer freely rotate. It means that, as Paul described, the moon as having slightly pear-shaped geometry. Now, part of this is the tide raised in the moon by the Earth's gravity, and the moon has been trying to rotate underneath its tides, as the Earth does under its water tides.
And we think, sorry I had to interrupt, I'm just trying to get it clear. We associate tides with water, and yet we don't see water on the moon. So when you're talking about tides on the moon, what are we talking about?
That's right. So these are the body tides. These are the tides raised in the crust and mantle of the planet.
Which actually swells and falls.
Yes, of course, a far smaller amount than does water, because rock is much more viscous. But it's enough for the Earth's gravity to get a lock on the moon, such that the moon is forced to rotate once each time that it orbits the Earth, and so from our point of view we only see the same face on it. But the tidal locking of the moon, so we see just one face, is perhaps the most obvious consequence of the Earth's influence on the moon. But there's another side to this coin, and that is that this tidal interaction between Earth and moon is causing the moon to recede. So it's currently drifting away from us at about 4 centimetres per year, as the Earth loses its rotational energy and cans it through gravity to the orbital energy of the moon. So the moon is receding, and this will actually continue until both planets become locked, so that the Earth rotates once a month, the moon rotates once a month, the Earth keeps the same face pointing to the moon, and the moon goes, but the month at that stage will be about 50 days long. And it won't happen for many, probably tens of thousands of millions of years. But eventually, when the Earth is tidally locked to the moon, this interaction will cease, and they'll both just keep their same faces to each other.
What'll it be like then? Will there be tides and stuff here still?
Well, at that point there won't be, because the two bodies will have stopped rotating with respect to each other. But it will happen. No one will live to see it. The sun will have become a red giant star before.
Oh, so it will have been blown up before that happens?
I think that is
true.
Well,
that's a relief. What can you tell us, Ian Crawford, about the composition of the moon and how we know its composition?
Yes, I can. So the moon is a small rocky planet, like the other planets in the inner solar system, Mercury, Venus, Earth and Mars. And I think although the moon is a natural satellite of the Earth and so strictly is a moon, from a geological perspective it's best seen as a small rocky planet like the other planets in the inner solar system. Now we know about its composition really from three main lines of evidence. The first is the observation of the surface of the near side, which we can see the Earth. Initially with telescopes, and then more recently with spacecraft, which have enabled us to make observations of the far side also. Then there's the density of the moon that Paul's alluded to, which is very important. The fact that it's got a density similar to silicate rocks, mantle and crustal rocks on the Earth. And then finally there's the tremendous geochemical evidence that's been produced by, or has been learned from studying the Apollo samples of the moon brought back 40 years ago.
What does that tell us? You emphasise tremendous since your
well,
area.
I think the scientific legacy of the Apollo program can't really be overestimated, and certainly for our understanding of the composition of the moon. If I just backtrack a little bit, just to put this in context, if you look at the moon from the Earth, and everyone should do so, it's very prominent tonight. There'll be a near first quarter moon this evening, and everyone should look at it. And if you look at it, you'll see the surface is not a homogeneous surface. There are light bits and dark bits. And dark bits are the so-called lunar seas, lunar mare, and the bright bits are the so-called lunar highlands. Now, what we've learnt from examining the Apollo material is the precise mineralogical composition of these. So Paul mentioned basalt, but in fact basalt is a volcanic rock, and the lunar mare, the lunar seas, are indeed basaltic volcanic rock. But the bright areas of the moon, the so-called lunar highlands, are made of another rock type. It's called an anthracite, and it's made principally of just a single mineral, plagioclase feldspar, which is a light-coloured rock, and it gives the lunar highlands its bright colour. So I think from a top-level point of view from lunar geology, it's studying the lunar samples have enabled us to see the moon as a geological body. And to understand its geology in detail, its mineralogy in quite great detail now. So those are the three main lines of evidence anyway, but I think it is the Apollo samples that primarily enable us to answer definitively the question, what is the moon made of?
I'm Julie Andrews, and it is my great pleasure to bring you Jane Austen Stories, the new show from the Noiser Podcast Network. I'll be reading Pride and Prejudice. We'll walk grand estates and take tea with well-dressed gentlewomen. But in this tranquil corner of England, not everything is quite as it appears. Listen to Jane Austen Stories wherever you get your podcasts.
Paul Merton, can I come back to you? There have been a number of different theories about how the moon was first formed. Can you run through one or two of the earlier ones and settle on the current one, and we'll explore that?
Well, one idea which was prevalent at 120-odd years ago was that the moon and the Earth split apart, the so-called fission origin of the moon. If you look at a geographical globe, you can see that the hemisphere of the Earth where the Pacific Ocean now is almost empty of land, and the idea was that the moon got sort of, as it were, plucked out of
scooped out
that area. Well, the Earth might have been rotating very quickly, and the two split apart, for example. Dynamically now known to be absolutely impossible. So didn't happen like that. Another idea is that the moon was captured from some distant time in the past. That there was an accidental encounter between the moon and the Earth, and the moon got sort of flung into orbit around the Earth.
So this planet is drifting across the universe, and it hits the gravitational pull of the Earth, and it stays there.
That sort of thing. Possibly not drifting across the universe, but drifting across the solar system anyway. Or maybe the moon and the Earth were formed together at the same time. Instead, the planets were formed out of little whirlpools in a nebula of dust and rocky stuff that was swirling around the solar system, little eddies in it, and maybe there was a double eddy where we were, and two things condensed both at the same time and next to one another, and so we have a moon and the Earth.
Is that the prevailing theory?
No. The theory now, which has been current since about the mid-80s, is a theory which is facetiously called the Big Splash or the Big Splat, which is that early on in the history of the solar system, there were a number of embryonic planets, and two of them encountered one another and actually collided. That one of them was the proto-Earth, and the other was a planet which is about Mars-sized and has been given the name of Theia, who was the Titan, who was the mother of Selene, the moon goddess. And these two objects collided, one against the other. Each of them was a planet with an iron core, and the two iron cores coalesced together into a single iron core. Each of them had a rocky mantle and a crust around them, and the rocky mantles and the crusts all crumpled up in this impact. A lot of the rocky stuff condensed back onto the Earth, but a lot of the rocky stuff condensed into a separate body, assembled itself in orbit. That's the moon. So the idea is that it was a chance event, a completely fluky, lucky, possibly unique event, quasi-unique event in the very early history of the solar system.
How long ago? What's the very early history?
Well, we're talking the solar system is 4.5 billion years old, and we're talking soon in the history of the solar system.
Ian Crawford, can we? That's now the most favoured explanation. Yes, you're nodding away, so it is. Why is it most? Can we just talk about this dust? Paul refers to this dust swirling around, and what dust? What's the dust?
Well, it's the consequences of the impact of this hypothetical planet Theia with the proto-Earth, as Paul said.
I thought this was before the impact, or this is after the impact.
There is dust. Dust is ubiquitous. Every time you get solids, you get dust. But there was dust that was formed rotating in a disk around the sun at the time that the sun was formed. Originally, that dust was from supernovae and other events in the celestial universe, in the stellar universe. And that created a dusty disk.
Can I just come back to the dust? So what's in the dust? I mean, the dust's in us, we know that, but what's in the dust?
If we're talking about the debris from which the moon formed, according to the giant impact theory, then that is a mixture of fragments of the Earth's mantle that was knocked off when this Theia object struck the Earth, and fragments of Theia's mantle, and it's all mixed together. Now, the reason this is currently the most popular theory, because it seems an extravagant theory at first sight. Why we've got these giant planets flying around like loose cannons in the solar system, and having to appeal to something that seems unlikely is not a scientist's first instinct. But the reason that lunar science has latched onto this theory for the formation of the moon really, again, is a consequence of our understanding of what the Apollo samples have told us. And it's this, that the moon is similar in bulk composition to the Earth, but not identical, and with two major exceptions. The first is the moon has, if it has an iron core at all, it's got a very small core, because its average density is so low, 3.5 grams per cubic centimetre instead of 5.5, which is the Earth's density. So your theory of the moon has to explain why the moon doesn't have a large iron core. And the other thing we've learnt from the Apollo samples is although the rocks and minerals are similar to those found on the Earth in many respects, they're extremely deficient in volatiles. So they're very deficient in water, they're very deficient in sodium, they're very deficient in all the chemical potassium, they're very deficient in all the chemical elements that have a low boiling point. And so that the giant impact theory explains both of these quite well, because when you have these two planetoids colliding, the cores, if they had a core, it merges with the core of the Earth. Then you've made the moon out of just the silicate component of the early Earth and Theia. And then collision will be a very violent, very energetic event, and the volatile substances will be boiled off and evaporated away. So what you're left with to build a moon out of is Earth-like stuff, minus the iron core, minus the volatiles. And so this explains the chemical composition of the moon well, but it's also, as Paul said, very consistent with our current understanding of the way the solar system was formed, with many planetlets, planetesimals in eccentric orbits crashing into each other.
Colonel Crawford, can I go back to the beginning of the serious study of the moon, which is credited to Galileo, with his observations in 1609, maybe a passing reference to Thomas Harriot, an Englishman who pointed the telescope at the moon in the same year, but his sketches weren't all that good and he didn't follow it through. Galileo's our man. How did his perceptions and affect people in such a profound way, because he did change the nature of discourse, didn't he?
It really did. And he was the first person to try and make sense of what you could see through the moon through this very crude optical telescope that was developed in 1609. And anybody can reproduce this sense of awe. If you just look at the moon through simple binoculars now, it changes from being just this sort of perfect disk with dark splodges on. You start to see structures on the moon. And particularly, as if, like Galileo did, you look at the dividing line between night and day on the moon. So that means on the moon, that's sunrise or sunset. It's where you get the longest shadows. And he could see that there were mountains on the moon, that there were these bowl-shaped depressions that we call craters on the moon, casting shadows. And from those shadows, he could start to estimate the height and just basically determined that the moon had a rugged landscape. It was similar to the Earth. It brought the moon much closer to something we could understand and we could contemplate. It made it much more, we could connect to it a lot better than just it being this sort of silver orb in the sky that we knew nothing about.
But it also brought reality into an area that had been almost mythological, hadn't it? The moon was the perfect sphere. It was up there, it represented all sorts of things, but its perfection and its spherical perfection were what mattered. And he said, no, it's like us, it's full of bumps and grinds.
Yeah, it's just like the Earth. It has a landscape, it has this topology. And yes, it is very much another planet that's very similar to the Earth, not some perfect celestial sphere in the sky.
Can you remind us of the initial impact of his views?
Well, again, it's this idea that the heavens were perfect, really, that had been left over from the Greeks and Aristotle ideas. And again, it's just challenging the way that we viewed the whole solar system. And of course, it's wound into his observations of Jupiter and of the Milky Way. It's just one of his many challenges to the view that had prevailed for centuries beforehand.
And we got closer and closer, Ian Crawford, and to the moon, and then we sent spacecraft there to look at big close-ups. What did they discover? How far in advance were they from Galileo?
I think it was a huge paradigm change in our understanding of the moon, because telescopic astronomy had made major progress studying the near side, but can't see the far side at all from the Earth. And so spacecraft finally enabled us both to see the far side and to make much more detailed observations of both near and far side, and eventually, of course, to land scientific instruments on the surface and to bring samples back. So most of this started in 1959. So only 2 years after Sputnik, within 2 years of Sputnik, there will be a series of very successful Russian spacecraft. The first flyby of the moon, the first spacecraft to hit the moon, and the first spacecraft, crucially, to take images of the far side, Luna 3, all occurred in 1959. It's revolutionised our knowledge, I would say. And
then the Americans took up the fight. It became a political struggle, didn't it, Paul? Well, a race, really. And Kennedy said he was going to put an astronaut on the moon by the end of the decade, and by the end of the decade, 1969, he did. What was significant about this?
Well, Russia, the Soviet Union as it was then, and the United States were competing, of course, in the Cold War, and each wished to demonstrate dominance in armaments, in strike capability against the other side. And space was an arena where that competition took place without actually having to go to war. The Russians...
Do you think it almost served a pacifying purpose?
I think you could argue that, yes. I think you could argue that, a bit like the Olympic Games, I suppose, a lot better to compete one nation against another in a peaceful way than to compete in a global war. Clearly so. The competition, of course, you can't completely compete. You haven't got the resources to compete in a completely unscaled sort of way, and the competition boiled down, in fact, to the USSR concentrating a lot on establishing a permanent station orbiting around the Earth, a space station like Mir, and the United States declared that it was going to go to the moon and establish the manned exploration of the moon. Kennedy set that as a goal for NASA, and much I might say to everybody in NASA's surprise. It came completely out of the blue for them. And they went ahead and did it, even though it was a very dangerous and risky thing to do.
Carolyn, can you tell us, would the discoveries made by the men who got to the moon, could they have been done by robots? What they brought back, could that have been done by robots?
Ooh, that's an interesting point. I mean, as Paul says, the primary reason for going to the moon was not scientific returns. However, again, as has been mentioned so far in the programme, these 382 kilos of samples of rock and soil that the Apollo scientists brought back were crucial in, building up this whole picture about the formation and the evolution of the moon. Now, strictly speaking, we could have collected those samples robotically. The Russians proved this with their lunar program. They were collecting lunar samples. And we could have perhaps collected them from a wider range of sites on the moon rather than just these 6 very safe Apollo sites. However, there were other scientific returns from the Apollo mission in that the astronauts set up scientific experiments on the surface, so measuring the seismic activity of the moon. They put a reflector on the moon where we bounce laser signals off it, and that's, for example, how we can say with such accuracy the moon is moving away at 4 centimetres a year. And to actually install experiments like that on the surface, there's a lot of human decision about where you site the experiment, how you align the experiment, how you check it's working. And that would have been maybe it would have been possible, but very difficult to achieve very efficiently through robotic means. So I think with any space exploration, you need the initial reconnaissance from the spacecraft, followed by the subsequent human exploration.
Yes, I very much agree with that. I mean, I think it's inconceivable that we would know as much about the moon now had the Apollo missions not occurred 40 years ago. I mean, it's true that the Russian lunar program, there were 3, Lunar 16, 20 and 24, returned with about 100 grams of lunar material each. But this is 0.1% of the 380 kilograms returned by Apollo. But in addition to that, the Apollo selection is much more diverse because the astronauts had such mobility, particularly in the later missions. It's a much more diverse set of samples, plus the installation of the geophysical instruments that Carolyn has mentioned. So some of it could have been done robotically, some of it not. But I still think, had it not happened, we'd know less about the moon now than we do.
Paul, Paul Mudden, I know you to come in, but could you also answer, jump to the 90s when the next spacecraft went, but you were going to say something.
Well, I was going to say that it seems to me quite common in the history of space exploration to see 2 completely different threads for the way science interacts with space exploration. In some cases, it's the science that leads. The scientists have a problem. They articulate the problem, they send a spacecraft to attack the problem. The fact that develops space capability is a kind of a spin-off from that everybody's very happy to accept, but it's a spin-off from the scientific drive. In the case of the Apollo missions and some others, you see some geopolitical sort of aim being articulated and being thrust towards. And the scientists hitch a ride on that. They exploit that opportunity. Somebody's going to go to the moon. Let's have a geologist go to the moon, and let's pick up what we can.
Carolyn, until relatively recently, there was thought to be no water on the moon. Now the water is somewhere on the moon, frozen and so on. What difference does that make?
It makes a huge difference to the potential for exploration of the moon, because if you could, anything you have to launch into orbit to the moon costs money. It's hideously expensive to send things out into space. So if you can find some of those resources that you need for exploration of the moon, especially a human presence on the moon, it makes things much more viable. So if there's frozen water on the moon, you have the potential to break it into its constituent parts, hydrogen for, say, rocket fuel, oxygen for air you breathe, water potentially for astronauts to drink or to use for crops. It just makes it a much more viable possibility. However, there's not that much water on the moon. I mean, yes, there's water on the moon, and if you'd asked us this 20 years ago, we would have said it was completely dry. We now know there's water on the moon, but it's not much. It's still drier than anywhere on Earth. It would take, probably like 1,000 tons of moon rock to squeeze out 1 litre of water. It's not very much at all.
Well, it depends. Slightly more than that. It depends. Most of the evidence for ice is in the polar craters which never see the sun, where it's always very cold and water ice is stable. 2 years ago, there was a spacecraft called L-Cross, which was deliberately designed to crash into one of these polar craters to see how much water vapor was released. And the estimates of that were 5% by weight in the regolith in the bottoms of these permanently shadowed craters. So 5% by weight, a cubic metre is about 1,700 kilograms of regolith. So I think you're 10 to 20 litres potentially per cubic metre, which is a lot. But of course, you are right, globally, water is very rare. So only in these very specific localities is there possibly quite a lot of water.
Yes, so it's only really in those parts in the craters that are in permanent shadow down by the poles. So you're right, but only these very specific locations. And those are going to be the potential targets if we ever do establish a lunar outpost.
Almoden, do you think the moon is going to be colonised?
I think it will be, yes.
Why? I mean, there doesn't say. Is it for other purposes, for the moon itself? Because a lot of people would say, well, what have we got out of the moon? There are these rocks, but they're more like rocks on the Earth than anything else. So what's coming from it that justifies the expense of going there in the first place?
Well, I think you have to take a very long-term view, and the long-term view is driven particularly from the former communist countries, from a Marxist ideology, where the outward exploration and onward progress of mankind is something which is inherent and inevitable in the progress of history.
So you're talking about ideology, not scientific research.
If you talk in terms of where mankind is going to go, is mankind going to go out into the solar system, then I think the first place to establish colonies outside of the Earth is going to be.
Is that just because it's a launching pad and it takes us a bit nearer Mars?
I think from our point of view, yes. From a Western point of view, I think that's right. From a Chinese point of view, I think there is inherent value in having a Chinese colony on the moon.
What's inherent about it? Just to show they can do it?
To show that they can do it, and because it's inevitable that they do it.
Oh, they think in the oh, I see. It's a theological.
Yes.
Oh, I see. I get it. Right. Carolyn.
There's also a view that the moon is a potential mineral resource. Okay, so a lot of the missions from the 1990s and in the 2000s are mapping the moon, trying to work out in more detail what possible resources are on there. And one of, perhaps it's a bit far-fetched, but one of the resources that some countries are interested in is the possibility of an isotope of helium called helium-3. So this is helium with 2 protons and 1 neutron in the nucleus. And we think it's being produced by the sun in enormous quantities, and the sun sort of sprays this out into space in the solar wind. And this soil, this broken down regolith that's on the surface, is very fine-grained material. It absorbs the helium-3 that the sun spits out. Now, so we think certainly in the older surfaces of the moon, you've got a lot of helium-3 trapped in, and this is important potentially as a very safe nuclear fusion fuel. And so the idea is that if it is found in vast quantities on the moon, we can potentially mine it and bring it back to Earth as a future very safe, very efficient fuel source. The problem, though, again, is you've got to go through a lot of the regolith to find the helium-3. So you would effectively be looking at strip mining the moon to get this fuel source out.
Ian Crawford.
Well, I think so. Looking for future resources on the moon is a possible justification for a renewed human presence on the moon. I agree with that. I think we can debate whether helium-3 is likely to be economically practical, and I personally have my doubts about that. But whether it is or not, I think there is a lot of scientific. The moon still has a lot to tell us about the history of this solar system and our place within it. And in particular, just as the lunar regolith is soaking up helium-3, it's soaking up the rest of the solar wind as well. So even if that's not economically useful, there is a record there of the evolution of the sun throughout the last 4,500 million years, potentially preserved in these regolith deposits, regardless of whether they're economically useful. They tell us a lot about the early sun that unless we build a time machine, we'll otherwise won't be able to access. And there's also the possibility that meteorites, just as we have meteorites from the moon, which I haven't actually talked about yet, but we do have meteorites from the moon that have landed on the Earth, it's highly likely that meteorites from the Earth will have landed on the moon. And there's a whole missing dark age in terrestrial geology, the first 1,000 million years of Earth's history, where the Earth has destroyed, eroded away its own crustal rocks. And perversely, if they're preserved anywhere, they may be preserved as Earth meteorites that were blasted off the early Earth 4 billion years ago, landed on the moon, where potentially they're being kept as kind of museum of solar system history, really, with a record of what our planet was like at the time life evolved on, or appeared, originated on the Earth. And we know very little about the conditions on the Earth at that early time, and the moon may preserve a record. It may also preserve a record just as it collects solar wind. There's some evidence that it collects molecules that have drifted out of the Earth's atmosphere and landed on the moon and become incorporated in the regolith. So there's a potential record there of the Earth's early crust, the Earth's early atmosphere, the Earth's early meteorite bombardment history. So actually, I think if we do go establish a lunar base or have a renewed human presence on the moon, there's actually a tremendous amount of science for these people to do.
Do you agree with that, Paul? Paul Murden?
I do, yes. I mean, it's the moon is a palimpsest. Everything that's ever been written over the history of the solar system is recorded on the surface there. There's the bombardment history on the surface, the history of all the meteors and asteroids.
That's because there's no atmosphere and things have to crash into it. They don't burn on the way through the atmosphere.
It's had no weather. So everything that happened has left its mark.
All those craters are...
And that mark has not been... eroded away. It has no plate tectonics, so the surface of the moon is not sort of churned over all the time. The history of the solar system is written there. If only you could read it.
It's wonderful to think of the moon. I never thought of the moon as a museum, but there it is. And if we dig far enough, we can find out things we don't know about the first billion years.
Yeah, I think this is absolutely a crucially important, reason for continuing the exploration of the moon.
Isn't there a sense that the three of you have got tremendous intellectual vested interest in talking up the importance of the moon? Because the more it gets there, the more fun you have.
Oh yes, we haven't even touched on. For example, I'm an astronomer. The astronomy you could do from the moon, far side of the moon, nice protection from all the radio signals from Earth. Nice long days. The potential scientifically of a permanent base on the moon is huge.
I'm cooler than that. I used to be responsible for funding scientific projects, and of course it's not just what you can do; it's how much it costs to do it, and what you would get if you spent the same amount of money in some other way. So I think you have to have the enthusiasm, you have to have the vision, and then you have to have the cold light of day where you look at the bottom line.
I see your eyes narrow for the first time. You put a scientific hat on, Paul Murden. And suddenly the conversation cooled.
It's what being associated with the civil service does for you.
Ian Crawford.
Well, I was just going to say, of course, Paul's right. If we're going to spend public money, we'll have to do so with our eyes open. But I think we talked earlier about China and international competition, and Apollo was a product of the Cold War. But I think there is a different model. I think we should be looking more now to having these expensive human space exploration programs as truly international efforts, truly global efforts, which can then achieve, in addition to all the science, a unifying potential for having a non-violent, as Paul mentioned earlier, way of collaborating scientifically over the whole world.
Well, thank you very much, Ian Crawford, Caroline Crawford and Paul Murden. And next week we'll be talking about the philosophical continental analytic split. Thanks for listening.
And when this edition was first broadcast, there was no extra content for the podcast. I can see, though, from the notes at the time, that as soon as the broadcast ended, Caroline Crawford produced a lump of rock from the moon for everyone to inspect. Anyway, this edition was produced by Natalia Fernandez, and we'll have another of Melvyn's most cherished episodes next week. In Our Time with Melvyn Bragg is produced by me, Simon Tillotson, and it's a BBC Studios production.
The figure's face was featureless, and its entire body was jet black.
I'm Danny Robbins, and throughout October, I will be sharing Uncanny Listeners, real-life ghost stories. That's one every single day as we count down to the spookiest time of the year.
Suddenly, all hell lets loose. The sound of glass smashing, heavy objects being thrown, doors being ripped off hinges. It was coming from the cellar. I looked up and was staggered to see a humongous black triangle floating silently over the rooftop.
Join me as Uncanny counts down to Halloween every day in October on BBC Sounds.
I'm Julie Andrews, and it is my great pleasure to bring you Jane Austen Stories, the new show from the Noiser Podcast Network. I'll be reading Pride and Prejudice. We'll walk grand estates and take tea with well-dressed gentlewomen. But in this tranquil corner of England, not everything is quite as it appears. Listen to Jane Austen Stories wherever you get your podcasts.